Well, I know you're all stoked for this.
That was wonderful.
Stoichiometry. Yeah, we're going to put together all that we had to learn about stoichiometry up until Christmas and beyond, I think, really, we went with that. And then we're going to put that together with all that we've been learning about gases, volume and pressure and temperature changes and all that. And, basically into one problem. And the amazing thing is it's how fast it comes back to you. You're actually a class behind or so. So I already did this with the other class. And you're going to be surprised how easy this really is. Stoichiometry of gases at STP for your notes. I'm only going to do 2 examples. I'm going to give you a worksheet that I will collect at the end of the first period. Then we're going to do another problem of a different type, also stoichiometry, but a little bit harder, and we'll do another worksheet then. So by the end of this double period, you will basically see everything you're going to see on the test for stoichiometry for the most part. Now remember, stoichiometry, when we did it back in the day, involved pretty much, it wasn't that long ago, about a month ago, but it involved pretty much everything we learned from the beginning of the year. We had conversions, we had moles, we used the periodic table, charges, equations, balancing, and conversion from moles to atoms and grams or whatever. Well, there's only one new thing in there. I bet you could probably tell me what it's going to be. Actually, you did it on the review packet because I didn't realize I didn't cut that out. What is it going to be?
STP.
Yeah, we're at STP. We could use what? Right, which is 22.4. Right. We now know that 1 mole contains not just the atomic mass in the periodic table, not just the 6.022 times 10 to the 23rd atoms or molecules, but we also now know that's how much the volume of a gas is at STP. So I could use that as part of my stoichiometry problem. And that's all that's new about this, as you'll see. Copy this example down, and we'll do that one, and you'll see how easy this is. I'll actually do 2 examples. And it's amazing how fast it comes back to you. I'm sorry. There's really not that much writing. It's not like it's a lot of notes. It's going to be mostly problems.
Yeah, but you're right.
Yeah, but that's it. It's not like A, B, C, 1, 2, 3, definition here, definition.
I'd rather have that.
I'm sure you would. And if we were doing that, you know what you'd rather have? Problems.
No.
Yeah. Mm-hmm.
Nah, I think you're right.
No, I know I'm right.
Nah, I don't think you're
See,
right.
I know I'm right.
Well, you don't know what I know, so therefore you are wrong.
Well,
Somehow, in her mind, that makes sense. All right. Now let's remind you. Let me remind you of. Whoa! Look at that. Woo! That's fast. We're going there by the end of the next period, but not yet. Not yet. This first one starts out a little bit easier. Remember how I taught you to do these? I said you read the problem several times. Whenever you have a word problem, and by the way, the book will make the word problems harder. It'll talk about in an oxygen tank, in a scuba diver. It'll throw a lot of extraneous information in there. I've got the bare bones, and it still needs to be read multiple times. First time I read this, what am I looking for in a stoichiometry problem? What do I want to find?
DMV.
Yes.
Just joking.
I want to find a Department of Motor Vehicles. DMV.
God, I was wondering what that meant.
Yeah. Anyway, so tell me what words, the words that tell me about what?
What reaction?
No, that's not right. I don't write the given information down because I don't have what yet. Yeah, the equation. I don't have the formula. I don't have the equation. I don't know the reaction that's happening. So tell me, remember how I did this? I'm going to underline the words that tell me about the equation. What will I underline in this first problem? Read. One more word I would need. The reaction of sodium with water. That's all I really need. Once I know that, I can do the problem. Sodium plus water yields. Guess what you're going to need to get out now? The common ion sheets. You don't have them out? Get them out.
No, not that awful.
Those sheets, reference sheets, keep you from having to memorize all this stuff. You should be happy to get
I
that.
love the common iron.
You should be. It should be your friend. The common ion is our friend. Fish are food, not friends. Oh wait, fish are friends, not food, right?
Fish are not friends.
Yeah, fish are friends, not food. Finding Nemo. All right, what does sodium plus water give me? Look at the common ion sheet. It does not give me sodium water, which I love when people wrote.
Sodium hydroxide.
Sodium hydroxide
Yes.
plus hydrogen, correct. All right, so sodium plus water yields sodium hydroxide plus hydrogen. I have to write them all correctly. Now, I'm not teaching you this for the first time, so we'll go through this very quickly. Sodium, water's H2O, NaOH. Yes, I still have to use the charges. Na plus 1, OH minus 1. Yes, I still have to remember diatomic elements. H2, hydrogen's diatomic. And yes, I still have to balance it. But it's not about that today. Today it's about doing stoichiometry with gases and STP. So I'm going to just do that quickly, and you should all know how to do that by now. There's your first step. Now, I go back and I read the question. This time I got to know I'm looking for what? What will I underline or circle or box? Yeah, which is?
4.30 grams.
4.30 grams of what?
Sodium.
Sodium. Okay, good. So I'll write that down. Now write small because you're going to have a bunch of conversions. Don't write big. I'm going to write down 4.30 grams of Na. And that starts me off on my journey of stoichiometry. Hey, the journey of 1,000 miles begins with a single conversion. Anyway, what goes to the bottom? What units? Grams of sodium. Make sure you keep putting down what they are. Grams of what? Because you'll get lost if you don't. I want to go for grams. I know that goes on the bottom because it has to cancel. But what people will do, try to go right to the answer. I can't do that. Because remember, stoichiometry is moles of what you have to moles of what you're looking for, right? That's the only thing these coefficients tell me is the mole ratio, not the gram ratio. So I got to get from grams of sodium into moles of sodium. I got to convert that into moles of sodium first. As you already, again, have seen in stoichiometry chapter. What goes next to moles every time you do a grams to moles conversion? 1 mole contains how many grams of sodium? I look at the periodic table, 22.990. And I have the first conversion. But don't hit equals. We're going to keep going like I've done before. Now this time, again, I may be a little lost, I may be a little confused, but that's why we do what I call following the units. I know moles of sodium have to go on the bottom. And I'm going to look back up there again and see who the heck it is I'm looking for. Because stoichiometry is moles of what I have to moles of what I'm looking for. I am looking for whom. No, whom, not what.
Hydrogen.
I'm looking for hydrogen. So I put moles of hydrogen on top. I cannot go directly to volume of hydrogen. I cannot go directly to liters of hydrogen. If I do that, I have not done stoichiometry. Every single stoichiometry problem must have that step. Moles to moles, where I use what to fill those moles in. What do I fill these in with? What numbers? The coefficients. H2's coefficient is a 1. Sodium's coefficient is a 2. It's right. It should be stuck in your head by now. And I told you how fast you would come back. It would come back to you. It's coming back to you pretty quickly. Moles. All right, I'm good. Now, by the way, nothing I've done so far, including this half of this next step, is new. Moles of hydrogen go on the bottom, obviously, because it has to cancel. Here comes the only new step. And it wouldn't even be here if it wasn't for one word that's different.
Volume.
Volume. Okay? I need the volume. That is not a problem. Now that we've had the last week, we learned what is the volume of 1 mole of any gas at STP. 22.4, and there it is. Get your calculators out. Make sure you can still multiply that out without making a dumb mistake, and we'll get the answer for that. Hurry up, because we have more to do. I am collecting both of these worksheets in classes. First one in the first class, second one in the second class.
Oh, no way.
So you have a lot of work to do.
Dude, are you trying to tell us?
I am. We have a lot of Friday, but we're working.
Okay.
Fridays were supposed to be easy.
Mm-hmm.
In Mr. Phillips' class, we watched 2 videos, and that was it.
That's nice. Now everybody knows that on the internet too. So
One was of these 2 old ladies.
we do your problem. All right, do the math for this. What do you get? What did we get? 2.09. Anybody else get that? And that's liters of hydrogen gas. Okay? How about that?
That's great.
That is great. Now that looks like that's a tough problem. It's got a lot of stuff in there, certainly, but we're going to find that the second period, we're going to go one step even beyond that. But let me do a second example of this kind of problem where you'll see the difference right off the bat. Okay, so it's not a huge difference for this second problem, but you will see a difference. Okay, you ready? Everybody got that copy? Good? All right, next one, copy this guy down. How many moles of sodium chlorate must be decomposed to produce 8.50 moles of, 8.50 liters of oxygen gas at STP? It won't look much different than the previous one. It's very similar. It's at STP. It's a stoichiometry problem. It's asking you for something. It's giving you something else. But I do this one for a couple of reasons. Two mainly. And you'll see what they are as I get through the problem. First step is obviously identical to every first step in a stoichiometry problem. I got to figure out my equation. What's going on with the reaction? What words tell me about that reaction? So if I'm reading this up here, you tell me. What words are going to tell me about this equation here? Okay.
Sodium chlorate and decomposed.
Exactly. That's all you need to know. Oh, all right. Sodium chlorate is decomposed. Once you know that, I'm going to shorten this up a little bit because it saves a little bit of space. Sodium chlorate is decomposing. I'm going to not write the words this time. I mean, you can and probably should for most of you, but you don't have to. Sodium chlorate decomposing is going to break up into what? Look at your common ion sheet. What does it break up into?
Sodium chloride plus oxygen.
Sodium chloride plus oxygen. Now, I have to remember oxygen is diatomic. I have to write all these guys correctly. I use, even though I didn't show it to you, I use the fact that he's +1. I use the fact that he was -1. I have to balance it with a 2 there and a 2 there and a 3 there. That gives me the same number of oxygens on both sides and everybody else. Okay? All right. So that's your first step. Now, the second step, when I look back up there, I'm going to look for the given information. And here's your first difference between the previous one and this one. My given information is 8.50 liters of oxygen. And that's different for this reason. The last one, I converted to, I used a 22.4 at the end of the problem. You're going to see that I'm going to use it at the beginning of this problem. What units have to go on the bottom here? Liters of oxygen. What's going to go on the top, you think? Remember, stoichiometry is still and always has been and always will be moles of what you have to moles of what, it's a mole ratio. So what's going to go on the top? I'm not in moles, I'm in liters. I need moles of oxygen. So I'm going from liters to moles. 1 mole contains 22.4. So here I'm doing that new conversion we were just learning in this chapter in the beginning of the problem.
Why don't you learn it in the beginning? Just wondered.
What's that?
Why don't you learn it in the beginning of just every all the other conversions?
It wouldn't have made any sense. I would have had to explain to you why, like I did in this chapter, and it would have made any sense to just give you that number out of the blue to give you this 22.4. We're on the chapter on gases. It makes sense now. I was able to explain to you why it's 22.4. Okay, had an Avogadro's principle, say equal volumes of gases, pressure, volume, temperature. Now we know that. That's one.
Okay.
Okay. There's a second reason I want to do this one as a difference. This one is a little bit different because last one had 3 steps. How many steps is this guy going to have?
4.
2. Why only 2? Well, moles of oxygen on the bottom. And I look up for the last time. I'm looking. What am I looking for? I'm looking for sodium chlorate. So moles of sodium chlorate. Oops. NaClO3 on the top. Moles of sodium chlorate on the top. Moles of oxygen on the bottom. All right, I fill them in with the coefficients like I always would. Sodium chloride's coefficient's a 2, oxygen's is a 3. And the reason I don't have another step beyond this is I'm done. The question asked me for moles this time. It didn't ask me for grams. It didn't ask me for liters. It asked me for moles. So I am done. I get my calculator out. I multiply them. I divide them. And I get what for an answer? She got 0.2. Should be 3 significant figures. 250 is it? 253. Moles of NaClO3. All right. Let me just hint ahead to you for the next class, after you're done with this first worksheet. I am going to change one thing for the next example I do. It won't be at STP next time. And that is going to make all the difference.